One of my favorite examples of Rossby waves actually has to do with El Nino Southern Oscillation. So if anyone isn't familiar with what El Nino is, or ENSO, it has to do with a disruption in the Walker cycle. So the Walker cycle is a climate cycle over the Pacific Ocean. So the trade winds blow the warm water from the eastern side to the western side, and it congregates. That warm water then evaporates, creating big rain clouds, and lots of moisture, and where we get the tropic areas near the Philippine Islands and all those the heavy rainforests there. Dry air comes up over the top and blows back down over the eastern side, creating the deserts that you actually see. That desert coastline in Peru is a really good example of that. And the pressure difference, where the warm water congregates towards the western side, and the cold water then allows the thermocline to bring up the nutrients of that water that's been down at the bottom of the ocean, collecting nutrients. It's very rich in phytoplankton. It's really good for the ocean ecosystems and things like that. So it brings that thermocline up. During an El Nino year, though, this cycle is disrupted, and it starts with, or at least what we think it starts with, is a weakening of the trade winds. So the trade winds weaken, causing less force to push that water across the Pacific Ocean, so it no longer congregates on the western boundary. It kind of is spread out. I mean, it kind of almost creates these two air circular cycles that you see here. So the water then kind of congregates towards the middle and evaporates up, causing rain over the ocean, and then you have dry air pulling out over both directions. And on the during El Nino years, this can have a big effect. It causes it can cause droughts in certain areas. It can cause lots of rain in monsoons in other areas. A big good example is during El Nino years, it's very common to have droughts in parts of Australia because they're right on that border. One thing I also want to mention too with El Nino years is there is no thermocline. Because the warm water hasn't created the right amount of pressure gradient for that cold water to come up, so that that nutrient-rich water that's at the bottom of the ocean stays at the bottom of the ocean, and it actually will affect reef cycles and how they are able to develop. So how does that tie into Rossby waves? So here's actually a really good example. So there's we look at Rossby waves in terms of sea surface temperature anomaly and sea surface height anomaly are some of the greatest examples. So from recorded El Nino years, 2014 and 1997. 1997 was a really big one. We'll see that one in just a second. But we can see, Rossby wave formulating across the Pacific Ocean so as the water moves west to east. So you could, if you're putting it on an XY plane, it moves in the negative X direction. We can see this beautiful, it's hard to describe exactly what it looks like, but it almost looks like a peninsula of warm water. And it creates this effect because of Rossby waves. It has the Coriolis force counteracting the sides of it as you go outside of the equatorial bounds, right? So the more further north or the more further south we get, we see the curving or curling of the water as it travels across the equator. So this is sea surface temperature anomaly in 2014 during December, when we know that the El Nino event is already on set. And then here's another example. This one I really, really love. This one shows you it very well. This is in 1997. So the maps are a little off skew, but we see right here is the sea surface temperature anomaly. This is the Rossby wave of that warm water, which is no longer congregating on the western boundary because the trade winds have weakened. It creates this beautiful Rossby wave where that warm water is just kind of spread out all over the Pacific. So I was actually able to find a really good image for the sea surface height anomaly data for Rossby wave for that same ENSO year in 1997. You can see that beautiful Rossby wave right there. And understanding some of the mechanics behind the Rossby waves, well, they're just derived from the Navier-Stokes momentum equations. We make two very important assumptions when we derive them. So we're assuming that that it is linear, and we're also assuming no friction. The linear equations then become just simply the acceleration, the Coriolis force, and the pressure gradient, where the pressure gradient, it has to do with the density, gravity, and eta, which is just a variation of the surface. The Coriolis force can be expanded, though. We can use something that's called a beta plane approximation in a Taylor expansion to kind of see how that Coriolis force changes as a function of latitude. So water, the wave right, essentially right on the equator will go just in a linear direction, you know, into the negative x direction. But any variation in latitude, either north or south, so specifically, so in the north direction, as the far north the wave goes, because generally waves are not, I mean, waves are multidimensional. They, you know, they have width to them. So if we have a wave that, you know, as it expands into any bit of the latitude into the north direction, it's going to have a clockwise effect on it, actually, which is got a restoring force basically from the planet's vorticity because the planet is spinning. There's this restoring force on the wave as it goes further north that has a clockwise rotation on the wave. And then the opposite is true as we go south, it has a counterclockwise rotation. So as a fun kind of project to kind of illustrate this a little bit, I created a very rudimentary animation for essentially different balls going into the negative x direction. And as you get further along the y, if I set it in an xy plane, right, as you get further along the y-axis, they have a spin on them. So I'm just going to play that real quick just to kind of show. It's very simple, but I thought it was kind of fun just to kind of give you an example of why we see that peaking effect. So it's just replaying on a loop. But the as we get further along the y direction, some of that momentum is stolen into the vertical spins. So I thought that was just kind of fun to kind of see how a Rossby wave might propagate. But yeah, hopefully you enjoyed learning about Rossby waves in ENSO.